So I'll make the introduction, and then Kurt, my student, is going to dive deep. So hello, everybody. My name is Constantinos Kolias. I'm an assistant professor at the University of Idaho. I'm going to introduce a novel way of side channel analysis for embedded devices through the fingerprinting that is totally unique, that is based on exclusively on synthetic electromagnetic signals, as opposed to the mainstream approaches where these signals are collected in real time. I am going to introduce the concept, as I said, while my student is going to describe the technical details later on. So let's start our presentation with a short journey through time. During World War II, the BBC News was broadcast to several countries across Europe, even to the Nazi-occupied territories. And each news program started with a live broadcast of the Big Ben tolling the hour. Now, ingenious German physicists found a way to determine the weather conditions in London based on these tiny differences in the tone of the ding-dongs of the Big Ben. This information was proven to be invaluable for the German Luftwaffe. And to the best of our knowledge, this was the first documented case of side channel analysis for adversarial purposes. Now, fast forward. Today, we live in the times of digital devices, the digital era, and side channel analysis is a valuable tool for even today. Indeed, it has been observed that digital devices such as embedded system emit a wide range of analog signals during their normal operation. Some signals may be acoustic, other signals may be thermal. And in our case, we are mostly interested and we are focusing on electromagnetic signals emitted from embedded devices. Now, while such signals are treated as noise, careful inspection may reveal meaningful details about the operation that is taking place on a device. Now, focus your attention on these two images. For example, the signal on the left gets emitted while the C program on the right is executed inside an Arduino device. Notice the peak, please. Such spikes are indicative of memory I/O operations. Now, notice their number. If you pay attention, you will see that we are talking about 15 peaks, and you can see on the image on the right that the loop gets executed exactly 15 times. We were able to learn important details about the structure and what happens inside the program just by observing the electromagnetic signals that get emitted from this device. In fact, the analysis of EM signals of a program has application to external and totally passive intrusion detection. Through side channel analysis, it is possible to answer the questions such as, is your code infected with malware? Some other applications, well-known applications of side channel analysis, include the detection of information leakage. In other words, we can answer questions such as, does your code leak information regarding, for example, important cryptographic operations that take place inside your device? Now, there are many challenges associated with side channel analysis. In the past, we have talked about a very important challenge, and that is the negative impact of environmental noise. Another challenge that is, I would say, greatly neglected from the research and industry, is also the process of capturing signals itself. It is a human-driven process that requires an experienced person to take position sensors in very specific locations. It consumes a lot of time, as you have to be present and fingerprint the entire execution cycle. And it is generally error prone as the sensor must be placed at the exact specific location that provides the highest quality of the signal. Moreover, software gets updated very often. Therefore, we have the need of capturing and recapturing and refingerprinting the electromagnetic signals of devices and of programs very often. The need is there, and so far, nobody has addressed how to deal with this issue. The state-of-the-art techniques mainly apply some sort of pre-processing to the signal through noise reduction, possibly, or normalization. But these techniques are, first of all, imperfect, and they may also introduce an error themselves. So far, to the best of our knowledge, like I mentioned, the issue is there, and it hasn't been addressed, and it hasn't attracted the interest of the research community. So we pose the question, can we avoid this step, or can we do something to optimize this step? And if given access to the source code of the program, the answer is obvious. We could try to synthetically generate something that approximates the electromagnetic signal that we would obtain in practice, in real life conditions. How would that work? How could we possibly implement something like that? Well, first of all, I suppose we could attempt to create a library of reusable building code to electromagnetic signal building blocks. Then we could align these building blocks according to the source code or according to the instructions that we have, and we could get that desired approximation of the electromagnetic signal. But before we jump to how we did it, let's first define what building block is for our purposes. One could claim that frequently used functions could be something as a building block. Another could say, no, we could prefer sequences of commands that are very often seen in practice. We chose to go with neither of these approaches, although potentially valid. We decided to choose the minimum structure possible to achieve the maximum generalization. And in this case, I think you can guess it's the assembly instructions that are supported by the CPU. In practice, there is a finite number, obviously, of such an instructions, and almost all programs, basically, that are written in any language and end up being translated into these assembly instructions. So in theory, after capturing and storing the electromagnetic signatures of these minimal quantities, the assembly instructions, it would be possible to create a library that we could take advantage, we could reuse, and in theory, this would work and we would be very happy. However, in practice, this is not the case. We have, unfortunately, a very serious challenge to overcome with this approach. And experimentally, we identified that the execution of instruction influences the shape and the amplitude and the characteristics of subsequent instructions. Obviously, the effect, and that's a good thing, diminishes over time. So subsequent X amount of subsequent instructions are not greatly affected by the execution of a specific instruction that we observe, but still the problem is there. This forces us to consider instruction at least in pairs. Now, let us provide an example to realize the practical implications of this restriction. Let us consider a very simple CPU architecture, which is the Atmel Mega CPU that is used inside the Arduino. That specific CPU architecture supports 123 assembly instructions. Initially, our task would be to simply fingerprint 123 instructions in isolation, right? However, after the findings of this research, we see that even if we consider the minimum, and that is fingerprinting instruction in pairs, The total amount of instructions that we have to fingerprint in advance is 123 times 123, which is roughly 15,000 cases. This creates a non-realistic case. Obviously, we could do it, but it is exponentially harder to start fingerprinting pairs, let alone triplets of instructions. And not only for this small type of CPU, but also for more sophisticated CPUs supporting many more a number of instructions. So at this point, I'll let my student, Kurt Vedros, describe the process and the framework that we relied on to find the solution to this problem, to overcome this challenge, and towards creating a totally synthesized version of an electromagnetic signal, in this case, with applications to anomaly detection. Kurt,
Dr. Kolias. Here on this slide, we present our findings for prior instruction. Okay, so once again, here we present our findings on the prior instruction influence. To reiterate, the electromagnetic signals of instructions can appear different when preceded by different previous instructions. This can be seen in the two figures to the right. The figures overlay two different programs, which we named Program A and Program B. They also showcase the values when executing similar instructions after executing a different prior instruction. As you can see in the top case, minimal to no difference in the same instruction is seen as the amplitude values of the prior instructions and the instruction operations are very similar, even though during this looked at instructions, they are the same. However, in the bottom case, much larger impact is visible. The amplitude of the two different prior instructions is dissimilar, and as such, the influence on the next instruction, which is a similar instruction between Program A and Program B, is very different. We also note that further back the prior instruction, the less it impacts the examined instruction. Furthermore, certain instructions impacts subsequent instructions less than others. So in this work, we assume that each instruction's execution is affected only by the immediately previous instruction for the sake of simplicity. For example, an add instruction's electromagnetic signal will be different when comparing an instance when the prior instruction is a subtract to when the prior instruction is a clear. To account for prior instruction influence, the overall structure of the library can be represented as the following matrix that we give to the bottom here, where the signal of the currently executed instruction n is given when under the condition of the prior instruction n-1. The structure of the matrix is similar to a dictionary format, where the key is the sequence pair of instructions of the prior instruction and the currently executed instruction, with the values being all the electromagnetic samples S of the instruction N when observed after the prior instruction N-1. So the overall framework to our approach is illustrated here, and it contains four main steps. The first step is to create a library of the basic building blocks. The basic building blocks, like we said before, it corresponds to the electromagnetic signature. And in our case, we relied on any frequently used instruction sequence. To be more descriptive, the overall process of this step is to capture the real electromagnetic signals from various programs whose binary codes are known, and as a collective, these programs contain a sample of every possible executed sequence. Afterwards, one of the full program's electromagnetic observations goes through a manual inspection to identify the location of each instruction. Then one by one, a copy of the electromagnetic segment of each instruction is extracted from the full program signal and we store it into the library. This process is repeated for every individual electromagnetic observation that we've captured previously. In practice, the captured process can be achieved with low-cost near-field probes or far-field antennas, such as the ones that we used, which was the EMRSS-RD Explorer H-loop electromagnetic probe. Step 2 is to create the synthetic signals. The process for generating the synthetic signals for a program, given the binary code, is relatively simple. First, the instruction in the binary code is identified. Then a random electromagnetic observation for the executed instruction that was captured after immediately executing the same prior instruction as in the binary code is retrieved from the library database. This extracted electromagnetic observation is appended to the end of a collective electromagnetic signal. And this process is repeated for each instruction in the binary code to create the full electromagnetic signal for the program we are trying to synthetically generate the signal for. Using this step, we can create any number of synthetic signals that we want for a given binary code. The third step is the fingerprinting phase, and it identifies the baseline or normal distribution of the benign programs for our anomaly detection method. To the end goal of discovering malicious electromagnetic signals, we relied on and extended a semi-supervised anomaly detection method. This method is based on the principles of transduction and hypothesis testing. Transduction is a technique of placing an example in a set of known observations and understanding if the example is a good fit. The overall algorithm to this step is presented to the right here. In further detail, during the fingerprinting phase, a set of electromagnetic observations for each benign case is extracted from an overall data set. The baseline of normal distribution for each benign case is evaluated by determining the strangeness or similarity score of each electromagnetic signal to the rest of the set of the benign cases electromagnetic observations. Specifically, a strangeness score is estimated by first calculating the distance of an electromagnetic signal to all observations in the set. Then the sum of the kth nearest neighbor or lowest distance is taken as the strangeness score. Furthermore, the baseline is the collection of the strangeness scores for every electromagnetic observation seen in the benign case. Each baseline for every benign case is calculated and stored in an overall data set and is accessed during the next step. So the fourth and final step is the anomaly detection phase, and it is performed during runtime. During this step, a new electromagnetic signal is taken from a device and is captured and is assumed to be running the same binary used to create the synthetic signals or baseline. After obtaining the newly captured electromagnetic signal, the strangeness score of the newly captured electromagnetic signal to each set is used to create each baseline that was used to create each baseline in the prior step is calculated. Afterwards, a placement value or p-value is estimated using the strangeness score for each baseline. The p-value is an indicator for how well the newly captured electromagnetic signal falls inside the given baseline. Next, a vote or verdict of if the newly captured electromagnetic signal is similar to the electromagnetic signals used to create the baseline is decided via a threshold value. This threshold value is used to determine if determines the verdict by seeing if the p-value is below the threshold, which in other words is within the normal distribution of the baseline, and then the electromagnetic signal status would be given as normal as it falls within that baseline. If the p-value is above the threshold for all the baselines, then the newly captured electromagnetic signal status is given as anomalous. To test our approach, we captured signals using the following setup as portrayed right here to the left. Our target platform we used was an Arduino Mega device equipped with an 8-bit AT Mega 2560 AVR microcontroller unit. We use this specific unit as it is a popular choice for research and real-time control applications. While the unit is executing the desired program, the electromagnetic signal is captured using an EMRSRF Explorer H loop electromagnetic probe placed on top of the CPU. As the emissions from the CPU can be very low amplitude, we had to amplify the signal using a Beehive 150A EMC probe amplifier. Finally, the digital format was saved using a picoscope 3403D oscilloscope and a laptop. We captured using a sampling rate of 500 million samples per second with a sampling interval of 2 nanoseconds and the average duration of the program considered to be less than 1 microsecond. For evaluation of our approach, we considered a scenario where a benign program with an execution path, with one execution path, is installed on the targeted platform and is comprised of 17 instructions being executed inside a loop. At some points, there was a need to create a modified version of the said program. For example, this emulates performing a software updates. Notice this process would normally generate the need for recapturing and retraining of the model and baseline. The target platform is expected to run either of these two programs, and as such, both should be considered as benign cases. Assuming we have already captured the original versions of the program, the task is to synthetically generate the electromagnetic signals for the modified version using the assembly code, avoiding the need to engage in a data gathering process from scratch while being able to detect anomalies as considered outside the norm of both possibly executed benign programs. In the slides, we can see the assembly code with the original program A to the left and the new modified version of program B to the right. For program B, the alterations from the original program is indicated in red. As you can see, for the first half of the programs are identical, but for the second parts, there are 6 new instructions that were altered and added. For our anomalous cases, we assume that a malicious entity performed code injections to our modified program, for which we tested 2 levels of detection. First is one that is easier to detect due to the presence of more injected code and is presented to the left. The easier version injects 4 instructions to the middle of our new program B's code. And the second one is presented to the right and is harder to detect due to the injections of only 2 instructions in the middle of program B's code. At this point, it should be noted that these injections are significantly minimal. And in reality, the attacker would probably try to inject a much higher volume of instructions in an effort to perform a more sophisticated and malicious operations. The following here is examples of the electromagnetic signal gathered for the benign case. Program A is presented to the left and program B is to the right. Each instruction's location in the electromagnetic signal is further identified with color variation. As such, different instructions can be seen at roughly index 400 to a level past 600, with the third to last instruction is just before the thousands and directs also being a different instruction. Here on this slide is examples of electromagnetic signals gathered for the malicious case. The malicious cases given below is similar to program B, except with the injected code, which is highlighted in light blue, For both cases, the injection point can be seen roughly before index 600. We collected 1,000 samples of each of the real observations for each of the benign cases and the 2 malicious injection cases for our data set. Furthermore, we also synthetically generated 1,000 samples of synthetic samples for program B using the steps 1 and 2 from the framework, using a library created from the electromagnetic signals of prior existing programs that are different from program A and program B and the malicious versions. To the top right is the electromagnetic signal of the synthetically generated version of program B, which we call synthetic B. To the bottom is a comparison of the electromagnetic observations for program A with synthetic B to the left and program B with synthetic B to the right. Synthetic B is visually close to program B for most peaks. There are some slight discrepancies as the electromagnetic peaks can fluctuate slightly, and we also only accounted for 1 previous instruction influence. Meanwhile, as you can see with the real electromagnetic observations of program A, it differs much more as several amplitude peaks can be seen to be different at much larger distances. We evaluated our approach with 2 experiments. The first experiment utilizes the real electromagnetic signals for program A and the synthetic signals for program B during the fingerprinting phase is what we used. And the second experiment used only the real electromagnetic signals for comparison. Additionally, each of these experiments went through 2 rounds of evaluation. One where the malicious signals were drawn from a pool corresponding to the easier case, and one where the malicious signals were drawn from a pool corresponding to the harder case. Furthermore, we evaluated using 10-fold cross-validation and estimated the strangeness score using the 10 nearest neighbors and a threshold from 0 to 1 with a step size of 0.001. For our metrics, we analyzed the AUC, the accuracy, and the F1 scores, along with the ROC graphs among the folds. In the table here, it showcases the AUC, the accuracy, and the F1 scores, and below is the ROC graphs in the same order as the results from the table. The first 2 ROC graphs are when fingerprinting with the real program A observations and the synthetic B signals for fingerprinting, and evaluating using malicious B easy in the first graph and malicious B hard in the second graph. In the last 2 ROC graphs are when fingerprinting using only the real electromagnetic signals for both program A and program B. Third graph is when evaluating using the easier to detect malicious versions, and the last case is evaluated when using the harder to detect malicious versions. For the results, using the synthetic data, the AUC was above 98% for the easy case and 95.1% for the harder malicious case. The results when using only the real electromagnetic data for during the fingerprinting phase was 99.3% AUC for both the easy and the hard case. For the accuracy and F1 scores, the use of synthetic signals achieved 90.1% and 90.6% respectively for the harder case, and 95.4% and 95.5% when detecting the easier to detect malicious cases. Using only real signals during fingerprinting, the results for the AUC and F1 scores achieved a near perfect result of above 99.5%. So in conclusion, the use of synthetically generated signals can achieve near perfect results while only incurring a very small penalty rates of about negative 1.3% to negative 4.2% for the AUC when compared to the use of using only real captured electromagnetic signals. Given the results, we conclude that relying on a database of real electromagnetic samples of assembly code instructions allows us to synthetically reconstruct an approximation of electromagnetic signals of a significantly large program with high fidelity. Thus, the proposed method can be used in the context of anomaly detection. More specifically, the proposed method of synthetically fingerprinting can effectively be used to train models relying, excuse me. When relying just on synthetic signals to distinguish between benign and anomalous cases with high accuracy, even for the detecting injections of minimal quantities of malicious instructions. This method can act as a basis for tackling one of the main challenges of side channel analysis, namely the manual capturing of electromagnetic signals. To further quantify the fidelity of the generative ability of our approach, the similarity of the generated signals with different types of real signals was evaluated and is presented in the following box plot to the right. The results indicate that the synthetic signals of program B created by our method are more similar to the real signals of the same program when comparing all the different programs that we captured. Both the malicious versions were drastically dissimilar despite the low number of malicious instructions that were injected. And interestingly, program A bears higher similarity to the synthetic samples in comparison to the malicious samples. And this is mainly because there's only 6 different instructions that were altered but not injected. But the two distributions on average have a very clear separation between program A and program B. Notice in these experiments, the similarity was evaluated using normalized Euclidean distance. As a final note for our future work, we intend to conduct a large-scale study for quantifying the impacts of different types of instructions on their compared to subsequent ones. Furthermore, we are looking into a more data-driven automated approach for signal generation by relying on more sophisticated methods such as generative adversarial networks or GANs for translating assembly code to electromagnetic signals. Some early results when gathering the electromagnetic signals or when generating the electromagnetic signals using GANs is portrayed at the bottom here, with comparison between the real observation, real captured electromagnetic signals and the generated ones. For the full signal is portrayed to the left, and a comparison when generating only the electromagnetic peak amplitudes are given to the right. This concludes our presentation. Thank you for your attention, and we would like to answer any questions that you may have.